Welcome to Olympiad Math for Year 4. This is Lesson 26, we'll learn mathematical games. Mathematical games are a contest of wit. Exploring strategies to win within the rules of a game is inseparable from mathematical thinking and methods. This lesson focuses on developing mathematical thinking skills through mathematical games. Example 1. Monks dividing steamed buns. 100 monks are to share 100 steamed buns. Each senior monk receives 3 buns, while every 3 junior monks share 1 bun. How many senior monks and junior monks are there? This problem can be cleverly solved using a grouping strategy. Each senior monk gets 3 buns, and every 3 junior monks share 1 bun. Let's group 1 senior monk and 3 junior monks together, making 4 people per group. Then, the 100 monks can be grouped into 25 groups. Since there is 1 senior monk in each group, the number of senior monks is 25. Then the number of junior monks is 75. The answer is there are 25 senior monks and 75 junior monks. The cleverness of this solution lies in appropriately grouping 1 senior monk and 3 junior monks together. In this way, 4 monks share exactly 4 buns, and the 100 monks can be evenly divided into 25 such groups, solving the problem neatly. If, instead, we grouped 3 senior monks and 3 junior monks together, then 6 monks would require 10 buns, but 100 is not divisible by 6, making this grouping method invalid. When using the grouping strategy, appropriate and effective grouping is key to solving the problem. Example 2. There are 2 piles of matches, with 26 and 28 matches respectively. Players A and B take turns removing matches from one of the 2 piles. On each turn, a player can take any number of matches from one pile, but must take at least one, and cannot take from both piles at the same time. The player who takes the last match wins the game. Assuming player A goes first, what strategy should A use to guarantee a win? Player A should begin by taking 2 matches from the pile of 28, making both piles equal with 26 matches each. From then on, whenever player B takes a certain number of matches from one pile, player A mirrors the move by taking the same number from the other pile. By keeping the 2 piles always equal after each round, player A ensures that they will be the one to take the final match. The answer is player A's winning strategy is to always maintain the same number of matches in both piles. Example 3. A deck of cards contains 54 cards. 2 players take turns drawing cards. Each player may take 1 to 4 cards per turn, and the player who takes the last card loses. What strategy should the first player use to ensure victory? Assume player A goes first, and player B goes second. Number the cards from 1 to 54. For player A to win, they must ensure that they take the 53rd card, leaving the last card 54th for player B to lose. Since each player can take 1 to 4 cards per turn, player A needs to force player B to start their turn at card 49, as B can then take at most up to card 52, allowing A to take card 53 next. To achieve this, A must ensure they take card 48. Tracing backward, we find that the key numbers for A to take are 48, 43, 38, all the way to 3. So, if player A takes 3 cards on their first turn, they will leave 51 cards on the table, starting the next move at card 4. Then, no matter how many cards player B takes, player A always takes enough cards to make a total of 5 cards per full round. This ensures that player A will always land on one of the key numbers, ultimately taking the 53rd card and forcing player B to take the last card. The answer is the first player should start by taking 3 cards. After that, on each turn, they should take 5 minus the number of cards the opponent just took. This guarantees a win. Example 4. Dividing peaches. Peaches are being divided among children. If each child receives 4 peaches, there is 1 peach left over. If each child receives 5 peaches, then 2 peaches are missing. How many children are there, and how many peaches? If giving 4 peaches per child results in 1 extra peach, and giving 5 peaches per child leads to a shortage of 2 peaches, then the total number of peaches is 1 more than a multiple of 4, and 2 less than a multiple of 5. Let's test small numbers. 4 times 3 equals 12, 12 plus 1 equals 13. 5 times 3 equals 15, 15 minus 2 equals 13. So 13 fits the conditions. It is 1 more than 12, that is a multiple of 4, and 2 less than 15, that is a multiple of 5. Let's verify with 13 peaches, we can find that 3 children can satisfy both conditions. The assumptions hold true. The answer is there are 3 children and 13 peaches. Example 5. Counting off game. 100 people are standing in a line. Starting from left to right, they take turns counting off 1, 2, 1, 2. Anyone who says 1 leaves the line. The remaining people then repeat the same process, from left to right, count off 1, 2, and those who say 1 leave. This continues until only 1 person remains. Which person in the original line is the last one remaining? Label the 100 people from left to right as 1, 2, 3, all the way to 98, 99, 100. After the first round, only people in even-numbered positions remain. After the second round, only multiples of 4 remain. After the third round, only multiples of 8 remain. After the fourth round, only multiples of 16 remain. After the fifth round, only 32, 64, 96 remains. After the sixth round, only 1 person remains as 64. The answer is the last person remaining is the 64th person in the original line. Example 6. The diagram below shows a 7x7 game board made up of 49 small square cells. The game is played by 2 players. A and B. Player A begins by placing a game piece on any cell in the bottom row or the leftmost column of the board, which is the shaded area in the diagram. Then, starting with player B, the 2 players take turns moving the piece. On each turn, the piece may be moved upward, rightward, or diagonally upright, at a 45-degree angle. The number of cells moved is unlimited, but at least 1 cell must be moved per turn. The player who moves the piece into the top right corner cell, which is marked with a triangle in the diagram, wins the game. As shown in the left diagram, if the piece reaches a shaded cell, the next move can take it directly to the top right corner, allowing that player to win immediately. Therefore, neither player wants to move the piece into a shaded cell, and both will try to force their opponent into doing so. From the diagram, we can see that if the piece lands on cell 1 or 2, the opponent's only option is to move it into a shaded cell, handing over the win. So, whoever controls cell 1 or 2 has a guaranteed path to victory. These 2 cells function like high ground in a strategic battle. Whoever seizes the high ground gains a decisive advantage. How can a player secure cell 1 or 2? A player can reach 1 or 2 in one move from a dashed cell. Therefore, one should avoid stepping into dashed cells, as doing so gives the opponent access to the high ground. Similarly, cells 3 and 4 are the second tier of strategic positions. Whoever reaches 3 or 4 first can force the opponent to step into a dashed cell or even directly into a shaded cell, setting up a win by either taking 1 or 2 or going directly to the mountaintop, the top right corner. Since the bottom row and leftmost column contain no strategic high ground, the piece initially placed by player A will not be on one of these winning positions. As a result, player B, who moves first, can seize the high ground or immediately reach the top, ensuring a guaranteed win. The answer is player B is guaranteed to win by taking control of key positions from the start. Example 7. On a snooker table, there are 15 red balls, each worth 1 point, and 6 high-value colored balls. Yellow, 2 points, brown, 3 points, green, 4 points, blue, 5 points, pink, 6 points, black, 7 points. Game rules for snooker. 1. The red balls must be potted first. After all the red balls are cleared, the colored balls are potted in ascending order of value, from yellow to black, to complete a full frame. 2. Between potting 2 red balls, the player may pot any 2 colored balls consecutively, returning each to its original position after potting. The player scores the value of each ball they successfully pot. Question: what is the maximum score Little White Rabbit can achieve in a single full frame? Assume Little White Rabbit pots every ball perfectly without any mistakes, and always chooses the highest scoring ball when allowed. For the first 14 red balls, each red is followed by pink and then black. It can get 196 points. For the last red ball, it is not followed by any colored ball, as the next phase begins. So the final scoring sequence is 1 red ball, then the colored balls are potted in order. Therefore, it gets 28 points. Total score is 224. The answer is Little White Rabbit can score a maximum of 224 points in one frame. Here are the practice problems for today. Thank you for watching and hope you enjoy your math today.